Hello everyone, David Giglio here with Ozen Engineering, and in this video I will give you an overview of using the electromagnetics physics module in Ansys Motor-CAD, and I use an interior permanent magnet as an example. So we start with choosing a model. In this case there are 4 physics options. On the top left we have E magnetic for electromagnetic, thermal for thermal heat transfer modeling, lab for motor performance evaluation, including generating efficiency maps and torque speed curves, and we have mechanical physics for evaluating rotor stress and noise, vibration, and harshness. So in this video we will focus on the overview of the electromagnetics physics model, and we can choose the motor type. There are these motor types available, and we will be using the brushless permanent magnet in this example. In particular, it is a interior permanent magnet type. All right, so we can start with a motor type, choose a motor type, and a default model will appear. We can develop our model for a particular design starting with the default model, or we can go to File, choose Open Template, and here we have various templates available already set up for a given application. So we see here we have applications for aerospace, electric mobility, such as electric vehicles, industrial applications, renewable energy application, and for this video we will use the E8 template with application in the automotive industry. Okay, and so this is selected. All right, so we have this model. Now there are, in the main menu, there are various tabs including the geometry, winding, input data, calculation, electromagnetics, output data, graphs, etc. I'll go one by one, just give an overview. Okay, so in the geometry tab we have other tabs within this tab, right? So we have the radial tab, which shows the parameters to set for the radial geometry parameters, right, including slot number, stator lamination diameter. And now if we right click on any one of these parameters, see, I right click on slot number, you see in the model it gives an animation of what this variable, what this parameter corresponds to, right? So again, I could click on the tooth width, it shows the tooth width changing. I could click on the slot depth, right click, see, we see the slot depth changing. So we can see any animation of any parameter by just right clicking. Okay, so we need to set all these parameters for the geometry for the radial dimensions. Similarly, before I talk about the other tabs, so in the bottom here we have geometry parameterization in terms of dimensions, where we specify a value for the dimension, and these parameters are independent from each other, and if there is if you enter a value that's not feasible, then you get error. So if we choose ratios, then there's like restrictions on the values you enter, and this is it ensures that you enter values that are feasible and to avoid any conflicts. Okay, so the values you enter are in terms of ratios instead of direct dimensions. Okay, now I was going to take you to, okay, we need to talk more about this. So we have the slot type. We have parallel tooth. We have different slot types: parallel tooth, square base. As you see here, we have all the other types: tapered slot. We can have ducts, different shapes: rectangular, circular, right? We have rotor type, right, for the magnets. This is interior permanent magnet motor, interior V-shape web, right? Where we have other shapes, other orientations, other positions for the magnets. Okay, and again, for the rotor ducts, we have these options here: circular ducts, shaft, spoke, arc ducts, rectangular ducts. Okay, now going to the axial tab. Axial geometry dimensions. This is the axial view, and these are the axial geometry parameters, right? So this is axial axial dimensions. So this is a axial view, right? And in here actually it says axial dimensions. So right on the right column we have the axial dimensions, right? So we could right click any of these and we see the axial dimensions change. And then on the left column are the radial dimensions, but shown in this axial view, okay? So we could right click any of these geometry values and we see how it changed in the radial direction looking at this axial view, okay? Now we have the shaft type, solid or spider type, radial ducts, either no ducts, or we have rotor and stator ducts, or individual rotor or stator, okay? And then we have this editor tab, which allows customization of geometry, where we can add parameters to be included in the rotor or stator, and we could give it a name, give it a value, right? So we could customize the geometry. And then here we have 3D view to show any 3D attributes of the stator, rotor, or the shaft. And move on to the next tab. Winding tab, very important. All these tabs are important, but in particular, this is, very important, right? We have the, let's see, winding tab, and then within the tab, there's a tab called pattern. So this shows the winding pattern, including the design, phase distribution, path type, number of phases, turns, throw, parallel path, winding layers, right? All these are typical quantities required in any winding design. And then within the same, on the winding tab, we have these other tabs below here for seeing the winding pattern in a radial view, right? So we can see the different coils here. So if we just want to look at one phase, we could just highlight here, phase 1. If we want to see phase 2, click phase 2, phase 3, right? Whatever phase you want to see. So let's look at phase 1. So we see here as it's 3 phase, right? 2 parallel path, 6 turns, 5 throw, and this is 8 pole. If we go back here, radial, number of poles, 8, okay? So we have 8 coils. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 magnet poles and 8 corresponding coils, right? And we can see that this 3-phase, but is 2 layers and it's 2 parallel paths. So 2 parallel paths, basically, it consists of 2 sections of 3-phase winding, right? And they're connected in parallel, right? So we can see the linear pattern here, okay? So we have, this is one section, right? 1, 2, 3, 4. This is one section of the winding, and another section shown, so one is in red, the other one is shown like a pink purple color. 1, 2, 3, 4 coils make up this section, and then these are connected in parallel. So this, where you see this end here with the arrow, will connect with the other end with the arrow, and then this end here with the negative sign will connect with the other end of the negative sign, right? And we can see the phasor diagram of the MMFs, right? So each coil carries current, produces a magnetic field, right? It's a source of MMF. So adding up the MMF contribution from each coil, we get this phasor diagram. So for each phase, we got eight coils, so there's 8 contributions to the MMF, right? And we can see MMF waveform. We can see harmonic distribution, right? And we can see, let's start with the electrical harmonic distribution of the MMF, right? So we are looking at here, the odd harmonics is what matters. So we have the first harmonic fundamental frequency, the highest amplitude of the MMF, and then we have the third harmonic, the fifth, right, all the odd. Now, the mechanical harmonics will be a multiple of the electrical harmonics, and the multiples are related to the number of pole pairs, right? It's basically the mechanical harmonics are the electrical harmonics frequency multiplied by the number of pole pairs. So for example, if here we have odd harmonics, so then in the mechanical view we have all the harmonics that are multiples of the electrical harmonic, right, using the number of pole pairs. So it's going to be 4, right? Because first harmonic times 4 is 4, and then the third harmonic times 4 is 12, and then the fourth harmonic, excuse me, the fifth harmonic times 4 is 20, and so on, right? So all the our harmonics multiplied by 4, then we get this mechanical distribution, all right? And then we can see factors for the magnitude. And moving on, let's see. So we have winding definition. We can see the coil style. So we have stranded or hairpin in this case, divider types, right? Wedge model, wedge definition, wire type, wire gauge, etc. Right? It's a lot of types to cover, so I'll start speeding up. We have input data. This tab contains tabs for materials, right? Materials used in the model for the different objects. We have settings, including for geometry, electromagnetics, calculations, and then calculations we could choose options for symmetry. Let me see, magnetics, we have options for core, stator, lamination, stacking factor, etc. All this is in the blog, right? So I'll just browse through. You could look at the blog for more information. And geometry options for end cap specification, end winding specification, etc. Okay, then let's move on. So we have torque calculation, mesh density, mesh control. So there's a lot of settings to configure here. It's important for the user to go through these settings and adjust them as necessary to create a model that's accurate and reflects the realistic performance of the machine. Right, so graphs, we have settings for this, settings for the losses. We could use either Steinmetz core loss model for the iron, Bertardi classical, Bertardi Maxwell. Any converter losses, we need to include it here, give it a value. So we have, these are general ones. Then we have bearing losses, right? Mechanical bearing losses, windage losses, AC winding losses. We can use analytical model, a hybrid FEA model, or a full FEA model. The hybrid model is a model that uses a combination of analytical and finite element analysis. And then we have other tabs, user preferences. Here, for example, we can import a DXF file. We could give that imported file an offset, and we can scale that imported geometry, right? So this is, if you want to import geometry, you go to preferences, import the file, and then we can offset it, scale it, rotate it as necessary. And then if you want to provide notes to your design, you can provide notes and have it saved. We have a tab for material database. Now here, if you want to model demagnetization, we would, here, for example, in this tab, input data, materials database, we click the material that we want to see any associated curves, right? So let's see, aluminum alloy is nothing, copper is nothing, right? But magnet has BH curves, right? So we want to see the intrinsic curve. We want to see the normal curve. We can see how the magnet is demagnetized, right? Depending on H, magnetic field strength, right? Where's the operating point? Where's the motor operating, and what is the magnetic field strength in the corresponding B value? Okay, so if we're below the knee, the magnet will be demagnetized, right? And there's different levels of demagnetization. And in the next video, I'll cover the magnetization workflow and application, right? So here we have other tabs, right? So for material database, we have physical tab. So we want to see thermal conductivity, we want to see specifications. These are thermal material properties. We see pH curve. We see, in this case, yeah, we can see M350. We can see the pH curve. So depending on what kind of curve you want to see, what material information you want to see, we need to click the appropriate tab, right? And some information right now is not populated, but if we want to, we could populate the information. We could reveal it, right? So let me go now to the next one. Calculation tab. Here's we configure the settings for the drive, different drive type, We could have a sinusoidal excitation. If you want to have a custom excitation, we could use that as well, where you could import a waveform. We have different winding connections. We have different directions for magnetization, parallel, radial, Halbach. We could set the temperature of the windings, the magnets, the shaft. We could set up thermocoupling, right? We could set the options for skew type for the stator rotor or leave it none. We could set the performance test, open circuit, on load. We have torque speed curve, demagnetization options, electromagnetic forces option. We can check parameters for self and mutual inductance. We could simulate transient sudden short circuit. And then we could also analyze centrifugal forces for rotor stresses calculations. And then once you set all the settings, just click solve, magnetic model, and in a few seconds or a minute, or however dense you set the mesh to be, that's going to determine how long it takes the model to solve, right? So the finer the mesh, the longer it takes to solve, but typically it's quick. And here we have the electromagnetics tab, FEA tab. So this magnetics tab contains 3 tabs. One of them is FEA. Here we see the field distributions for flux density, vector potential, current density, different various electromagnetic field results. We could see them in a plot here, either magnitude, or we could see a vector field distribution. And we need to solve this as well, which is, again, solves quickly within either seconds or a minute, a few minutes, it depends, okay? Depends how complicated and how fine the mesh is. And we can apply all these settings to reveal any specific details of the plot that you want to see. And then for FEA editor, we can adjust the positions of magnets or the B field for one magnet. So we can add a multiplier if you want to adjust the remnant flux for a given magnet. We can adjust the orientation degrees. So there's different things that we can do here. Now, again, if we import a DXF model for the geometry file for the geometry, we can apply settings here for that as well. And here, FEA path, we can determine or edit the paths for the FEA calculations, right? In this case, it's a 1/8 symmetry model, as shown here with this slice, this pizza-shaped slice. We can, instead of 1/8 symmetry, if you want, for whatever reason you want to use, higher, you want to see model more than just 1/8 slice, you can model the full model, or you can model a half symmetry, right, depending on what you want. And output data, we have we can see results for the drive, right, electrical quantities, some also a mix of electrical and mechanical quantities, right, for the drive, the electromagnetics quantities, including the torques. We can see input power, total losses, efficiency, power factor, Coggin period, right? Different flux linkage, DQ axis, quantities, right? Various quantities, electrical and mechanical, inputs and outputs, phasor diagram, right? For sinusoidal excitation only. So if we have sinusoidal excitation, we have this phasor diagram tab where it allows us to see the phase quantities in this phasor diagram. We have equivalent circuit quantities to look at and to analyze. We have flux density values, air gap flux, stator tooth flux density, etc. Losses, quantities for the core loss, the winding losses, various losses in the motor model. And here we can see winding data, right, for cross-sectional areas, current densities, linear dimensions, okay, resistances, etc. And this tab is a miscellaneous tab, which shows statistics of the mesh nodes, mesh elements, air gap mesh layer is used. Materials tab gives all the information of the material used in the model, right, to get the results. And we have this graphs tab, shows, it contains 3 tabs to show results in terms of data tables, in terms of plots, in terms of harmonic bar graphs or spectrums. And we can see currents, terminal voltages, torques, torque graphs, plots of air gap flux density, and plots of flux linkage on the load. And we could do sensitivity studies where we can set a range for a parameter, right? Give it a minimum, a maximum of step size, and simulate the model, solve the model for this range for the parameter, and see how the output changes based on sweeping this parameter, right? That's for a sensitivity study. In a future video, I'll do an example of this. And we have an option for scripting using Python. And here's just an example script. So using scripting will give you full control of the motor model, and analysis give you full control of the options, the settings. You could do optimization, sweeps. There's basically no limit. So you have total control for the motor design, modeling, analysis, and post-processing. And finally, we have settings for using Python or actually Visual Basic Script. Apply script control, right? And that is all for this video. Contact us to learn about our simulation capability and request a demonstration for us to show you how we can help you with your engineering projects. Ozen Engineering Inc. is an Ansys Elite channel partner